Okay. We'll wait one more minute and then we'll start. And I'll just start talking about what we're going to do today, though. Okay. So today we're going to go through a couple of the mechanisms, and I'm going through the mechanisms because I think they'll help with the synthesis problems that we have. So on your test, you're going to get a synthesis problem that's very similar to what I have on the screen right now. So they'll give you a compound and they'll ask you what two things do you need to, or what reagents do you need to make this compound. And so it's important that you know the reagents that you need for each reaction, for the different reactions, and because there's specific things that react in each reaction, each named one, that you have to list out as reagents. And then if you don't list those out and you found another way to make that compound, it'll be counted as wrong because we're asking you what are the reagents to do it through malonic ester synthesis or through aldol condensation. After we're done with that, we'll go through some synthesis problem that I think is very likely to be on your exam, just because I don't know, she always puts malonic ester or acetoacetic ester synthesis on her synthesis page for this exam. And so that's exactly what we're going to be working through. Does anyone have any questions about anything like updates for TA sessions, anything class related so far? Make sure you ask those questions in the chat. I'm gonna give some more updates. I sent you guys the YouTube videos for the review for exam 3. I think those are really good to look at just because they help you differentiate between the different reactions, the named ones. Let's see. So if you didn't get those, make sure to DM me on GroupMe or email or whatever you want. And if you're not able to make any of the sessions, especially any of the sessions previous to this one and that relate to exam 3, make sure to email me with your proof of work for those worksheets and I can send you the answer keys. Okay. All right, so then I'm gonna start now. We're gonna do the mechanisms first. And so first one we're gonna do is Dieckmann, which is an intramolecular Claisen. So for Claisen reactions, you react two esters together. So here, the reason that they're related to each other, Dieckmann and Claisen, is just because Dieckmann is going to have the two esters that are required in that same compound. Just as we have it in the reagents, we have two esters in that same compound. So we start from two esters. And we'll see what we will always be expecting in our products after we do this reaction mechanism. First step is always do the acid base part of it. So you're going to deprotonate your alpha hydrogen. And you can deprotonate either or since it's a symmetrical molecule. So I'm going to have this base go ahead and deprotonate this hydrogen, and we'll put those electrons onto the carbon. Okay. Now you have your nucleophile, and so whenever you have your nucleophile, now you're looking for your electrophile, and we know that it's usually our carbonyl carbon. We won't be able to attack the carbonyl carbon that it's right next to, just because that's a lot of there'd be a lot of angle strain. I don't think that's possible if we were to attack that one. So we're gonna attack the one on the opposite side. And so when we attack that electrophile, we can't have 5 bonds to carbon, so we'll resonate upwards. Oops. Yeah, I started drawing it as a linear compound, but as soon as you attack from here, you are making a cyclic compound. So with Dieckmann's, you're always going to have a cyclic compound in your product. So then what you have to do, I like to number for my nucleophile all throughout the compound until I get to my electrophile, which is my carbonyl carbon. And so I stop at that number and I see that there's going to be 6 carbons in my product for this step. A 6 carbon cyclic molecule. I can number it however I want on this starting structure, as long as the substituents are all good and where they should be. So this whole structure right here on carbon number 1, we didn't mess with at all. So that's going to be coming straight off of carbon number 1. I'm going to put ET right here. And on carbon number 6, we resonated the oxygen upwards. The electrons onto the oxygen upwards. And we also have oxygen with an ethyl group on it, directly connected to carbon number 6, just as it is right here. This is directly connected to carbon number 6. Okay. And so from here, we're going to want to reform the carbonyl. And let me check if that's good, because sometimes the Claisen and Dieckmann reactions are a little weird because we have to protonate along the way. So let me just check if this is all good. Check. Yeah. So we're going to reform the carbonyl. And honestly, if you get confused with the steps, I would start naming what you're doing in each step. So like the first step was just to deprotonate. The next step was nucleophilic attack. This step is reform carbonyl. And so let's reform the carbonyl and kick off that leaving group. So everything else stays as is. And if I reform the carbonyl on carbon number 6, just get the carbonyl by itself. And then OET is just my leaving group, so it goes off. But we are not done here, so I can't really explain too well why this step occurs, just because, I don't know, I always had a lot of trouble with it. But this is your expected product. But before you're done with the mechanism for both the Dieckmann and the Claisen, this will only happen with the Dieckmann and the Claisen. The leaving group pretty much is going to come and grab on to the alpha carbon hydrogen, the most acidic hydrogen, and give us a conjugate base. Like this. And then the conjugate acid, or I believe it's H3O plus, because we're adding H3O plus in this mixture. Yeah, this H3O plus is going to go ahead and protonate this right here. And so we get the compound that, again, we had thought that was originally going to be our product. I guess I kind of remember the explanation for this. So when we make this product right here, it's stabilized by a lot of conjugation. So let's see. This is sp2, 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 and sp2. So a lot of conjugation, whereas if we didn't have that and we just left it like this, there'd just be less conjugation. So since this right here, although it doesn't look stable because it has a charge, it's actually more stable than the neutral compound. And so this would be kind of our primary product. And that's why we need to use H3O plus at the very end to force it to become what we want it to be, so which is a neutral product. I don't think that'll be a conceptual question, but I think this is just like why we have to do this in the mechanism, even though it looks kind of redundant because we're kind of going back to the same thing. Any questions so far for the mechanism part? Again, I only think that happens with the Dieckmann and the Claisen. And then at the end of it, each one of them, you'll get a 1,3 ketoester. So it's called a 1,3 ketoester because between those carbonyls, they're 3 carbons apart. One of them has a ketone and one of them has an ester, so 2 functional groups. Would this reaction be a mechanism question? Both are fair game. I'm sure she kind of listed out what she's gonna have for mechanism questions. I don't really pay attention too much to that stuff just because I'm not taking the test anymore. So you should ask your classmates which mechanisms they're focusing on, because I'm pretty sure she lists them out while she's lecturing. But again, all fair game. This is the main thing we should be concerned with as well, though. What you need in the reactants and what you will need in the products or will find in the products. And that's how you can kind of prove that you're correct in this mechanism and in your product. Any other questions? Okay. If there's no other questions, I'll continue. So I didn't put the Claisen on here just because, again, it's like the same mechanism. The only thing that's different is it's not on the same compound. Those 2 esters aren't in the same compound. So that's what's good about it. I guess we'll move on to the aldol condensation because Michael is going to combine 2 reactions. So aldol is one of them that they'll use. So let's go to the aldol condensation mechanism. Again, first step is always find your base, put its charge, and deprotonate where possible. And so you have 2 compounds right here. She doesn't necessarily say you have to deprotonate this one or this one, but you need to figure out which one is the most acidic and where you're even where it's possible to deprotonate. Because this hydrogen right here, it's not an alpha hydrogen. It's not an alpha hydrogen because it's not a non-alpha carbon. There's no alpha carbon here. So that's not a possibility to deprotonate at all. But then I look at this compound right here and I have 2 alpha carbons, but there's only 1 alpha hydrogen. There's 3 alpha hydrogens, but on one side, 1 carbon. And so on this carbon, I'll deprotonate this hydrogen and make my nucleophile. So this is my nucleophile right here. Okay, so we have our nucleophile. We have our nucleophile, and so always second step is to attack our electrophile, which is usually our carbonyl carbon, and we'll resonate up from here. This is nucleophilic attack. So our product for this part of the mechanism will look like this. Just keep in mind where everything is. So I would say pay attention to the carbonyl carbon here. It has an oxygen, has an oxyanion, has a hydrogen that was from the original aldehyde, and it has a new bond, which I'll color in a different color. This red color represents the new bond to the nucleophile. So that's your intermediate right now. So from here, when you see a carbanion, or I'm sorry, an oxyanion, the next thing you do is kind of neutralize the compound. So you use your conjugate acid. And so I made a conjugate acid using this over here where ethoxide deprotonates the hydrogen and you get this. ethanol. So the electrons on this oxygen are going to go ahead and deprotonate ethanol. We'll call this the protonation step because we're protonating what we want to be protonated. Protonation. And we create this compound next. This was the new bond that we had originally. So this, let me see if I can remember the name. I'll have to look at my notes though. What's it called? Beta hydroxycarbonyl. Beta hydroxy carbonyl. Some notes I would write for this, for aldol condensation. You can use whatever combination of aldehyde or ketone. Whatever combinations, you can use an aldehyde with an aldehyde, a ketone with a ketone, or an aldehyde with a ketone. Nonetheless, those are the reagents that you need for the aldol condensation. For the next step, you have to make your beta hydroxy carbonyl. And then there's an additional step, and this is the condensation. The condensation step. So when you lose water, because that's condensing, and you'll make the alpha beta unsaturated compound. And it's important that you know these two steps because on your test, they can just say, what's the product for? Okay, yeah. You can just say, what's the product for the aldol? What's the aldol product? And then they can also say, what's the aldol condensation product, which is going to be two different things. So right now we have the aldol product, but now we have to condense. So you're going to do the E1CB part of this mechanism. Which means I have to make the conjugate base of this right here. And so how do you do that? You use a base. You're going to deprotonate your most acidic hydrogen, which is the alpha hydrogen right now. And you're going to make the conjugate base, which is the enolate. And so from here, now we're able to kick off what is our leaving group, even though it's a bad leaving group due to the thermodynamic sink and everything that she explained during lecture, it can leave because it makes a very, very stable product. And therefore the leaving group will leave. And this is our aldol condensation product. Okay. Again, when I was learning this, I was overwhelmed by all the mechanisms, but I think if you can just learn how to differentiate between them and just notice how a lot of the mechanisms are similar to each other, it's just the endings that differ a little bit, then I think you'll get used to it and I think you'll be fine for the exam. But any questions for this one? Does it matter where the double bond ends up? It does. Because yeah, it definitely does. It should end up between the alcohol and the alpha carbon always. So I don't know, it is important. Yeah, that's why the mechanism is important too, because it helps you keep track of where the alcohol should be. And therefore you'll know where the double bond should be as well. Also, if you put the double bond anywhere else, there wouldn't be any conjugation. So here, luckily though, we have a whole bunch of sp2 carbons right next to each other, and that's therefore it's very conjugated. So if we didn't have that double bond there, then we would like be able to tell that something's wrong, because our product should look like an alpha beta unsaturated compound, and it should be very stable due to conjugation. And you also wouldn't be able to put a double bond between these two, because carbon already has all its bonds. Any other questions? Okay. Let's see. Dieckmann, Claisen, Aldol. Okay, then we'll do Michael. Michael is our next reaction. Let's see if I had, yeah. So for Michael reactions, let's see. We need an enolate plus an alpha, beta, carbonyl compound. Those are the things that we need in our reagents. Our alpha beta unsaturated compound is called our Michael acceptor, so that's just a side note. And we're forming a 1,4 addition product. Let me see what that looks like really quick. We'll see what we make in the product, because I'm looking at my notes and it looks funny, but we should know the mechanism, so that's good. So you know that you need an enolate and an alpha beta compound. So we have our alpha beta compound, and let's make our enolate. So as usual, find your base, put its charge, find your most acidic proton, which you're in between both of them. You could deprotonate any one that you want. And you make your enolate, which looks like this. Then I'll draw my Michael acceptor nearby. This is the same thing that we have in our reagents. It's just kind of flipped backwards, so they're the same thing. And here it's a 1,4 addition, and therefore you're not attacking your carbonyl as you usually have been. So let me just keep doing that. So here you're gonna do your 1,4 addition. So 1, 2, 3, 4. We're attacking the 4th position. So nucleophile comes and attack your 4th position, but your carbon has its full octet, so you're gonna have to break this bond. And I'll put my carbons on the carbon itself instead of resonating all the way to make another enolate, just because it's going to be easier along the way. But yeah, from here, it's going to be important that you number your compound. So let's see how you want to number it. I always number from my nucleophile to where I attack my electrophile. So 1, 2, and I'll number around a little bit. I'll number all the way to my carbonyl. I'm gonna draw the basic structures. So I'll do the square first with its carbonyl compound, and I'll label just so I keep everything in mind. So this was carbon number 2, this is 3, and this is 4. We made a new bond to carbon number 1, which was our alpha carbon. And then the last thing we need to take into account is the electrons that are on the carbon due to us resonating them on the carbon. So that's our compound so far. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Trying to remember what two. Does anyone remember what two reactions that I'm using? I know that it's an Aldol reaction and something else. It's an Aldol reaction. I want to get it down. I have my notes with me though, so it's good. Okay, I was getting confused with Robinson and Michael. So yeah, we're almost done with this one now. Last part of this one is just pronate that. Using the conjugate acid that we have there, or just the acid that we have there, ethanol. You can deprotonate ethanol, and then you make your stable compound. It just looks like this. And so for your Michael reaction, you need an enolate, which we created, and you need your alpha beta compound, which is your Michael acceptor. And you will create a 1, 2, 3, 4, 5, a 1, 5 diketone. Because at positions 1 and 5, you have 2 ketones. Any questions for this one? This one can get a little complicated if you had wanted to do your like enolates, the resonance form of these enolates, because then you would need to tautomerize. But if you just keep this kind of resonance form instead of doing the full-on enolate, then you won't have to go through that step, and it'd still be counted right. In my opinion, this is the easier step, but again, you can form the enolate and the enol and then tautomerize, and that'll be fine too. Any questions? Okay, I'm gonna skip the Robinson annulation for now. If we have more time, then I'll go back to it and I'll quickly work through it. But I'm gonna stick with the ones that we just did right now because these synthesis problems, in my opinion, are really good for differentiating between the reactions, especially now that we have our notes on what we're expected to be making with what reagents. So we're gonna skip to the synthesis, or this part, number 2. So number 2 says provide the reagents necessary to make the following compounds. So starting with A, we're talking about malonic ester synthesis. And for malonic ester synthesis, you are always going to start with diethyl malonate, which looks like this. So this is diethyl malonate. So if I'm asking you what reagents for malonic ester synthesis, you need to have that, diethyl malonate. Okay. Again, this one wasn't the one that we covered in our mechanisms previously in this page, but I'll show you the tricks that you need to know. So let's just start with an example though, before we start into these. So for malonic ester synthesis, just a quick reminder of what it looks like. You usually start with a deprotonation step. So in the deprotonation step, you would deprotonate this alpha carbon, hydrogen, because it's the most acidic. And then you have step number 2, which usually adds some sort of carbon group using an alkyl halide. And so here I use alkyl halide of, I forget what the name is, methyl bromo? I don't know. But you're adding a total of 1 carbons to the alpha carbon. So that step 2 would just look like this for the product. And then step 3, they can totally keep adding more groups to the alpha carbon, but what usually happens is they do H3O+, which H3O+ will convert only one of the esters into a carboxylic acid. So step 3's product should just look like this. And then you have step 4, which is your last step usually in the malonic ester synthesis, which is heat. And heat does your decarboxylation step. And so in your decarboxylation step, you turn that one carboxylic acid that you made previously, and you're going to completely remove it because it's decarboxylating. You're going to get rid of CO2. And in the process of removing this carboxylic acid, you're removing CO2. So then you're just left with this as your product. And so what you will notice, I'll draw what our original reagent looked like really quick. What you should notice in your malonic ester synthesis is that one of your ester groups is going to completely come off because you're going to make it into a carboxylic acid and then remove it by decarboxylation. And you should be kind of focused on what's on the alpha carbon now. And so identify what your alpha carbon is. My alpha carbon, it's the only one that's there. And you will have to see what groups are being added to this alpha carbon. So for example, let's see how I can work backwards with this. If I didn't give you any of these reagents, I know that at some point I added 1 carbon group because that's the only thing on my alpha carbon. And so, along the way, you'll do an alkyl halide that's just bromine and just a methyl group. And then I can do something like this too. Let's see. I can give you a synthesis problem like this. Which has an ester. Let's do this and this and this. And so how many alkyl halides am I going to be using for this reaction? How many of them? Yeah, you're going to be using 2 alkyl halides because there's 2 separate groups attached to that alpha carbon that we're talking about. Identify your alpha carbon, and these are the 2 groups that you're going to be adding somewhere along your mechanism. So that's what we're going to be focusing on with this synthesis problem right here. So again, malonic ester synthesis, you always start with diethyl malonate. So this is our first step. I'll look at what we're trying to make, which is this right here. And what's interesting, yeah, that's interesting. I don't think I meant to put, it's fine, we can work through it. First thing you do, identify your alpha carbon. And then notice all the things that are attached to that alpha carbon, all the different things that are attached to that alpha carbon. So it's one methyl group, and then it's one whole sec-butyl group. So these are two different groups that are attached to my alpha carbon. And so these are the steps that I'm going to need in order to make that product right there. So step number 1 always starts with deprotonation. And once you deprotonate, you can add one of your alkyl halides. So I'll do the easiest one so far. It's just adding that methyl group. So I'll do bromine CH3. And then you automatically added this alkyl group onto it. Those are the first things that you need to do. You just need to keep adding those groups. Step number 2, there's still another group. I'm sorry, step number 3, there's still another group that you want to add. And so you're going to deprotonate one more time. Because you need a nucleophile in order to add that sec-butyl group. Okay, so you deprotonated. And now you need to write that whole sec-butyl group. And be careful with dropping carbons. But there's a total of 1, 2, 3, 4 carbons coming off of that alpha carbon. So you're adding 4 carbons. You need 4 carbons in your reagent. And that is good because you have 1, 2, 3, and 4. So you added the groups that you wanted. And now you want to focus on getting rid of that whole other ester part of it, which you know that you can do that by doing step 5, make one of them a carboxylic acid using H3O+. In step 6, use heat to just completely take off that carboxylic acid. And then last step, just because that's what I'm giving you right here, it's a carboxylic acid instead of an ester. We don't usually do that. I think maybe I got confused or maybe I did that on purpose, but just to make that product, what it would be step number 7. How do I make that final ester group into a carboxylic acid? Yeah, H3O+ again. Because now you only have one ester group, and you can make that one ester group of carboxylic acid. Any questions so far? Happy faces if we're good. I post these recordings. I usually don't record, but since I think this is a pretty important worksheet, I'll post this one on my YouTube channel and I'll send it out to you guys. Why did we need the other amount of H2O+? Just because that's what I gave. Again, usually in your product for malonic ester synthesis, it's just going to be another ester. But since I gave you OH group, then our last part is going to be H3O+. And another reason is because H3O+ will only convert one ester into a carboxylic acid. So when we did this one initially, it converted the one that we had leave. And then we had that ester left, another ester left. And so we used another equivalence of H3O+ to convert that last ester into carboxylic acid. Because again, it usually converts them one at a time. I don't know why it does that. Yeah. Of course, of course. Okay. Cool. So then we'll work on the next one. Still malonic ester synthesis, and therefore you need diethyl malonate in your reagent. So this is already a couple of points that you can have on your test because you know that it needs to have this. And then identify your alpha carbon. So this is my alpha carbon right here. And how many carbons are attached to that alpha carbon? There's a total of 2. So somewhere along the way, I'm going to have to use an alkyl halide with 2 carbons on them. And so how do I convert this reagent into the one that I desire? Always use a base first to make my nucleophile. and then you're going to use your alkyl halide with the desired amount of carbons, which is 2. So this is my 2 carbons that I'm adding. I am going to, since that's like the only thing that we need to add, we do need to also get rid of this ester group, and so we completely forget about any other alkyl halides and move on to just taking that ester off, which we know we can do by converting that ester, one of the esters, into a carboxylic acid, and then removing the one that we converted into carboxylic acid. So by doing these like steps 3 and 4, we completely remove this group, which was desired. And again, usually you would stop there because you're making an ester, but since I'm giving you this synthesis specifically just to work with it, the last step is H3O plus, because you'll only have one ester left, and H3O plus usually converts one ester at a time into a carboxylic acid. So last step, H3 plus. And that's the end for that one. Any questions? Okay, cool. Next one is the Aldol condensation. I'll copy some of the notes that we use for the Aldol condensation reaction, which is pretty much just these right here. For every Aldol reaction, you can use an aldehyde with an aldehyde, or a ketone with a ketone, an aldehyde with a ketone, whatever mix you want, as long as it's those 2 functional groups that you're starting with. So let's try, there's pretty much tricks to them. I don't think I need to explain anything like how I did with malonic esters, since we already kind of went over this. What I want you to notice from, like, let's see the previous reactions kind. Yeah. So what I want you to notice from these, and I'm pretty sure she said it one time in a lecture, is that if you find your alpha carbon, you're going to cut your whole compound at your alpha carbon, and you're going to notice how you can clearly see your 2 parts of your reagents. So this whole part, your benzaldehyde, you can easily see. And then the other part, that's your enolate, is very clearly visible as well. So what I would do is when you identify your alpha carbon, cut it at that alpha carbon and just attach the oxygen to, let's see, to the side that doesn't have the carbonyl, basically. Because one of them already has the carbonyl and you need 2 carbonyls. And so you would leave it to this side right here. So then when I look at my aldol condensation, again, the tricks for it are identify your alpha carbon and cut your compound at that alpha carbon. So you'll have one compound, one carbonyl compound that has a ketone. And then on the side that doesn't have a ketone, that's where you'll add your oxygen. So I'm adding my oxygen to this side over here. You can write it like identically, exactly how it is on the problem. But these would be my 2 compounds in order to make my aldol condensation. And that's almost all you need, but remember, in addition to your 2 aldehydes and ketones or mix of them, you also need a base. So you can just do NaOET. And let's see if they need, yeah, that's all you need pretty much. So it's just these 3 things that you needed to make that compound right there. Any questions for this one? Aldol condensations are very important because you're going to see them in biochemistry, and they might not say it in like chemical terms, like this is your aldol reaction, but you'll be able to identify it just through names. So like names of enzymes, like aldolase. You're like, that sounds familiar, and that's because they're creating something or breaking something using aldol, aldol condensation, or the reverse reaction. No questions? What's the word between use and combo? Oh, it's whatever. WTV. Use whatever combo of aldehyde or ketone. Mm-hmm. Okay, so let's move to the next one. Is the second reagent supposed to have an H? No, it won't, because at a point in the aldol condensation where you need to protonate something, it's gonna be the conjugate acid of this. So you don't need the acid right now, because along the way it's just gonna make it. And then of course you also need the base because you're gonna need to make your enolate. Oh, I get what you're saying. So like this. Yeah. I made a mistake. One of them is supposed to be the aldehyde. Thank you. Thank you. Okay, cool. So again, identify your alpha carbon, cut it down, draw your compound with the carbonyl, and the side that doesn't have the carbonyl, add that oxygen to it. So these are your two reagents that you need to make that compound up there, but you also need a base. And so these are the three things that you should list down. Happy faces are good. Questions in the comments if we have questions. Okay. Let's see. Okay, these are good because you're going to be able to handle two of these synthesis problems just by learning one of them. So Claisen and Dieckmann are going to be very similar in how we synthesize the compounds. So I already have pretty much what you need to know to synthesize those compounds. You're going to cut the bond between the ester and the alpha carbon. Let me see. Cut the bond between the ester's alpha carbon and the carbonyl. So I don't know, hard to decode just by looking at that, but once I talk about it, it's gonna make sense. So find your ester, which is this part of the compound, and then find that ester's alpha carbon. So this is my ester's alpha carbon. And so what you're gonna do is, after you find that ester's alpha carbon, look for the carbonyl that's next to it. So this is the carbonyl that's next to it, and this is the bond that you're gonna be cutting pretty much. And so immediately we can see one of our products is just going to be an ester with a methyl group attached to the alpha carbon. And the other one of our products is going to be this part of the compound, but instead of that bond that was originally there, it's going to be also an ester. Because for a Claisen, you need to react two esters together to make a 1,3 keto ester. So again, identify your ester group. So this is my ester functional group, and then label the alpha carbon for that ester functional group. Then find your other carbonyl group, which is the one right next to it, without the ester, and cut that bond in between. And so you'll have that whole original group of ester, and you need two esters in order for a Claisen reaction to happen. And so then this bond is going to become the OET part to make that other ester. A little confusing with the words, but that's pretty much the trick to know the two reagents that you're going to use to make your desired product with Claisen. Okay, and then we can try that again with another one. Find your ester. This is my ester right here. Find the alpha carbon and the carbonyl that it's attached to, and you're gonna break that bond. And so for Claisen reactions, I forgot about that. Yeah, I'll put that at the end just so that I can get this one down really quick. So you'll have that original ester that you had. And you need another ester in order for a Claisen reaction to happen. So these are what your two main carbonyl components should look like. Again, for a Claisen reaction to happen, you need two esters, and you will make a 1,3 beta keto, 1,3 keto ester. And then, yeah, Sarah had a good point. In order to have all of your reagents there, we'll look back at this Claisen reaction. Yeah. And you need your base NH3O+. And so along with what we just wrote, you'll need a base and H3O+. It's the same thing over here, a base and H3O+. Any questions so far? Okay, cool. So then since we know what to do with the Claisen, we're gonna go ahead and skip to the Dieckmann. And notice how I have the same note here because the Dieckmann is gonna be the same thing. You need two esters, but this time they're gonna be on the same compound, and you're gonna make a 1,3 keto ester. Just as you see in these compounds right here, you have 1, 2, 3, 1,3 beta keto ester, 1, 2, 3 beta keto ester. 1,3 keto ester. So again, same rules. Identify your ester. Identify the alpha carbon for that ester. Then the carbonyl without the ester. And split it from there. So you'll draw your basic structure. Because again, you're not splitting anything else. And you'll draw the rest of the compound. So this whole group is attached to the benzene ring, but same thing with this part over here. They're just attached on different carbons. 1, 2. 1, 2, yeah. And you need two esters, so on the one that didn't have the ester originally, you add OET. And then again, the same things. Step 1, you need a base. Step 2, you need H3O+. We'll work on the next one, but it's the same thing. Identify your alpha carbon. Separate your ester from your carbonyl. And then see how they're connected to each other. So you know that you split it up through there. but this whole group is attached to the benzene ring. So that's what we should write it as. Let's see. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. So 4 has our original ester. And then the top group, again, you can number it however you want as long as it helps you. 1, 2. There's 2 carbons coming off of that carbon next to it. 1, 2. It's a little cluttered. Yeah, it's a little cluttered, but I wanted to make sure that they're next to each other regardless. Let's see. Is everyone okay with these? Do you have any questions, or do you want to practice any other one? Like I can give you more practice problems right now though. So Dieckmann, Claisen, Aldol, malonic ester. Do you need to practice any of them? Is there a solvent for these? No solvent. Yeah, not that I remember. Can you do more Dieckmann? Yeah, I can give you another one. Make sure to put this one. Yeah, let me give you one more of Dieckmann. Let's see. Let's see. Let's see how easy this is to make. So I'm just gonna do cyclic structure. And that should be good. And so show me what compound you need to make this group right here. Do we add a carbon bond when we split them? You don't add a carbon. You add a bond though, because there's that bond to oxygen, or carbon bond. A bond between carbon and oxygen, yeah. These would be the new bonds. So again, the one that we're doing right here is this one to Dieckmann. What compound do you need in order to make that? How come it wasn't added for the first problem? Let's see. Oh, yeah, I accidentally added a carbon. Let's see. I think I accidentally added 2 carbons. 1, 2, 3, 4. Yeah, I accidentally added 2 carbons. So I got confused with my numbering. Let's just try this. Because I numbered this one number 1, and that got me confused. So that's carbon number 1. This is 2, this is 3, and this is 4. Yeah, by the way that I numbered it. Yeah, the way that I numbered it in the beginning kind of confused me, but when I closely look at it, it's a bit better. And again, you can number however you want, as long as it helps you. But that's the actual answer for that one. I just added 2 carbons accidentally. Thank you for that. Let's see if I did it with the other one. No, the other one should be good. Yeah, the other one should be good. For this compound right here, same thing. Identify the alpha carbon, find your ester, and find your carbonyl compounds, and break the bond between the alpha carbon and just the regular carbonyl, not the one with the ester. So from here, I am going to number all the way around like this. And so I made a chain with 7 carbons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Carbon number 1 was the ketone part. I'm sorry, the carbonyl part, the one that was by itself. Carbon number 7 contained the original ester. And you know this is a Dieckmann, so you need 2 esters on your compound. And that's exactly what you'll do with the carbonyl that looked like it was by itself. And that should be the right reagent that you need in order to make that Dieckmann, the Dieckmann product. And you could have done the same numbering system over here if you had wanted to. For example, just as we had done over there, we were numbering, I can start with anything. And I can number all the way around to account for all my carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and make sure that everything is good. Any questions so far? Okay. I'll do the Michael one because this one should be a little easier for you guys to get. Kind of, it's almost very similar. Those also have the NOET. Yeah. Sorry about that. I keep forgetting about that. Step number 1, NaOET. Step number 2, H0 plus. Thank you. The synthesis problem should be okay for you guys to figure out by yourselves just because it's very similar. The thing I'd keep in mind is that instead of having a carboxylic acid group at the end, you have a methanol there. And so you're gonna have to take into account like doing a Williamson ether synthesis at the end. But just by looking at the starting material, what kind of reaction am I supposed to be thinking about right now? Yeah, malonic, the malonic ester one. Yeah. Perfect. Okay, so then you guys got that one. And I'll probably send the finished worksheet after this anyways. But then let's do the Michael reaction. So the Michael reaction will always result in a 1,5 diketone. So we can just prove that. 1, 2, 3, 4, 5. So at carbons 1 and 5, we have 2 ketones. Just check this one as well. Carbon 1 and 5, we have 2 ketones. So if they ever give you a synthesis like this, you can just identify what your product looks like, and then you'll be able to see like, oh, this is the type of reaction that I'm probably going to have to do because I know that this reaction will result in this. So, and then remember for your Michaels, you need an enolate plus an alpha, beta, and saturated compound. So you can do this in a lot of ways, I think. I would probably, again, always find my alpha carbon. And you can think of it as you're breaking this bond and putting the electrons on that double bond. That's not actually what happens in the mechanism, but I feel like that's an easy way to see what your two products are going to look like. And so by doing that, again, you identified one of your alpha carbons, and you can have there's a lot of ways to do this one. I can show you a couple of ways that we can do this one, but identify your alpha carbon and then move away from that alpha carbon and put those electrons onto the next carbon, between the next carbon. So just by doing that, make something like this, plus this. And those would be the two things that I need to make this microwell reaction happen. So you have your enolate, or the thing that you're going to make your enolate, and you have your alpha, beta, unsaturated. And then just to finish it off, let's see what the microwell requires. Microwell requires the base and its conjugate acid in 2 different steps. So I do base and conjugate acid in the second step. But again, following that same kind of strategy to find your product, you can also do it this way. Find your alpha carbon, the one that's kind of connecting those 2 carbonyl groups. So you find your alpha carbon on this side, break that bond and put the electrons on carbon next to it. So this is another way that you could have made this product using this alpha carbon. That was really scary. Nice. And using that alpha, beta, unsaturated. So those are 2 ways that you could have made that product. And on your test, they'll only be expecting you to do one way, but we know all of the ways that you can make this product, and so either way you chose to do it, we'll mark it correct if it's correct. Any questions for this one? Okay, so I'll give you like a minute or 2 to try out that next one, and then you'll confirm with whatever I write down. And then while you're working on that one, I'm just going to quickly finish the mechanisms for the Robinson so that you have something to work with. Again, I'm going to let you take a screenshot of this so you don't have to pay attention to it right now. If you're done with the last one, bear with me. I'm trying to get this done so I don't have to work through it later. You can start copying this one down if you want. Let's see, where did this become the Aldol? There you go. Just the whole thing with all the notes for that one. I'll give you a couple seconds to screenshot that if you would like. If not, I can go back to it later. Okay. Okay, so let's see what you guys got for this. Identify your alpha carbon, put the electrons from that bond onto your double bond. And so my two groups that I should have are this one and the unsaturated part that looks like this. Or you could have done, let's do it in this color. You could have identified your alpha carbon here, put your double bonds there. And so that means this would have been your enolate. And this part would have been your alpha beta unsaturated. And so this is the results if you did it through the green way, and this is your results if you did it through the red way. But with both of them, you need NaOET and HOOET. And I think it's good if you can do the two products, both the red and the green, just because it's more practice. So any questions on anything that we've done so far, including this one? Feel free to take a picture of it if you haven't already. Okay. I'm gonna scroll to this one. Again, keep asking your questions if you have any questions, but I'm gonna keep scrolling so that you can take screenshots of all the notes. Okay, moving on to this one with the Robinson annulation that we didn't get to do together, but there's all the notes in there. Just know that Robinson annulation combines the Michael reaction. So that's the first thing you do. And then you have the Aldol, and then you have the Aldol condensation. So it's a lot of steps for that one. But as long as you know your mechanisms for both the Michael and the Aldol and the condensation, then you're able to put them together. And I'm pretty sure she always puts this one on the mechanisms page. So just because it combines all the reactions, so know how to do these reactions, especially when they're all combined in Robinson. Final thing, again, if you have any questions, put them in the chat. I already sent out YouTube videos for this exam. I'm going to quickly not go over it. I'm just going to give you the answer to this one. You should have known that you're adding two groups to it. So let's see. First step is always deprotonate. Second step is to add one of your groups using your alkyl halide. So I'll put the methyl. Third step is if you still have other groups to put, you'll deprotonate again. And again, using an alkyl halide, you'll add that second group. After you're done with that, you're going to remove one of your carboxylic acids using H3O plus and heat. And then you would be left with pretty much this
Sorry. With seventh step, use any base that you want. So it's you can use NaOH. That would be your preferred base. And then eighth step is you use another alkyl halide so that oxyanion that you created with the acid-base interaction between NaOH and your carboxylic acid, you can now do an SN2 reaction between that oxyanion and your alkyl halide. And it'd be a methyl group that you would add on. So you can do something like BrCH3. Can you see the last one really quick, please? My iPad died, but I can send you a picture of it when I can charge it again. Yeah, I'll send you all pictures of it. I'll send you guys the post for this YouTube recording and everything just so that you have it for notes. But yeah. Alrighty. So then we're done for this session. If you have any questions about class or anything, I'll be here. But yeah, make sure to look at all your videos, all your practice exams and everything, and you'll be good for the test. We'll see you guys on Monday.